Hello, and this one being this video, is going to be on directional derivatives and the gradient. All right, so what is a directional derivative, right? This is not something that we have in Calc 1. All right, so given a function f of x, y, so we're going to talk about functions in two variables initially. We have defined partial derivatives already, right? The partial with respect to x is the rate of change of f as we vary x, and the partial with respect to y is the rate of change as we vary y. Next thing we're going to discuss is the rate of change of f if we allow both x and y to change simultaneously. So how do we do that? So if you look at figure 4.39 of the textbook reproduced below if you're looking at the page, we see this nice function. And let's suppose we have a function AB in the domain of f. And we have, so f of AB, we're going to choose a direction to travel, and we're going to measure the direction using an angle theta, right, measured counterclockwise in the xy plane from the positive x-axis, i.e. how we normally define theta. Okay, and we're starting at the origin as usual. We're going to travel a distance h from our point AB. So the direction traveled is given by the unit vector cosine theta I plus sine theta j, which we'll call u. And so the z coordinate of the second point on the graph, which isn't actually pictured in the figure, is given by z equals f evaluated a plus h times cosine theta, b plus h times sine theta. The slope of the secant through those 2 points is given by this equation here. So it's the standard slope of a sequence. As the slope of a sequence is the standard slope of a line, right? Rise over run, so to speak. And to find the slope of the tangent line in the same direction, right, we take the limit as h goes to 0. So suppose z equals f of xy is a function with domain D. We can let AB be a point in said domain and define the unit vector u as cosine theta I plus sine theta j. The directional derivative of f in the direction of u is given by, it's denoted with a capital D, and it is equal to the limit as h goes to 0, well, of that slope. And so that's the definition. Of course, in practice, this formula is not too much fun to apply. However, we can find a formula that's much easier and user-friendly. So to do this, let's define x to be a plus t cosine theta and y as b plus t sine theta. We'll define a new function g of t to be f of xy. Assuming that the partials of f with respect to x and y both exist, we can use the chain rule to find g prime of t as follows, right? G prime of t is going to be the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. And so that is going to give us the partial of f with respect to x. Oops. Wow, I'm getting excitable. Times cosine theta plus the partial of f with respect to y times sine theta. If t is equal to 0, then we can see that x is equal to a and y is equal to b. And so we get that g prime of 0 is going to be the partial of f with respect to x at our point AB times cos theta plus partial of f with respect to y again at our point AB times sine theta. But by definition of g prime of t, we also know that g prime of 0 is going to be the limit as t goes to 0 of g of t minus g of 0 over t, but plugging in what g of t is, right? That's f of a plus t times cosine theta, b plus t times sine theta, minus f evaluated at ab, all over t. But that is just the definition of the directional derivative of f. At AB. So there you go. So therefore, we can just write the directional derivative of f at any point in the direction u is going to be the partial of f with respect to x times cosine theta plus the partial of f with respect to y times sine theta. And we can also write this using component form as the directional derivative of f in the direction of the unit vector u is going to be the dot product of the vector composed of the partials of f with respect to x and y, and take the dot product of that with u. By the way, if u is not a unit vector, then we have to normalize it before we apply that equation. Okay, let's do a couple of examples. And I'm making this a short video, well, as short as whatever this is going to be. So let's find the following directional derivatives. Let's find the directional derivative of f evaluated at the point 2, 0, where the function f is x e to the xy plus y, and u is the unit vector in the direction of theta equals 2 pi over 3. All right, so what do we do first? First, let's just find u. So what is u? Well, u is just cosine theta I plus sine theta j. And so that's cosine of 2 pi over 3 I plus sine of 2 pi over 3 j. Cosine of 2 pi over 3 is negative 1/2, and sine of 2 pi over 3 is root 3 over 2, and there's our unit vector. Next, we have to find the partials with respect to x and with respect to y of our function. So the partial of f with respect to x, where we take the derivative with respect to x. So notice and remember that we're going to have a product rule in the first term, and the second term, well, the second term is 0 when we take the derivative partial with respect to x. I feel like I dropped an x there. So I'm going to get e to the xy plus x squared e to the xy. And when I evaluate that at the point 2, 0, I get e to the 2 times 0 plus 2 squared e to the 2 times 0, also known as 4. Wait, I totally did that wrong. That should not be an x squared. That should have been an x times y. Oops. See, professors make mistakes too. And sometimes the computer doesn't want to work, even if you've literally just put the thing on. Okay, so let's try that again. 1. All right, partial of f with respect to y. So I have d dy of x e to the xy plus d dy of y. And what is that going to give me? Let's see. Now I'm going to get x squared e to the xy plus 1. So I get 2 squared e to the 2 times 0 plus 1, which is 5. There we go. All right, so now we're done, right? Just plug in the formula. So the directional derivative in the direction of u of our function, evaluated at 2, 0, is going to be 1 times negative 1/2 I, not I. Oh wait, 1 times negative 1/2 plus 5 times root 3 over 2. However you want to write this, negative 1 plus 5 root 3 over 2, and that's our answer. Okay, let's do another example. Let's find the directional derivative of f, different f this time, in the direction of u. So f of xy equals x squared y plus y squared x, but this time I want it in the direction of the vector v, given in component form as 3, 4. Okay, so here, right, v is not a unit vector, so we need to normalize it. What is the norm of v, or the magnitude of v? Should be able to figure that out fairly quickly, right? We get 3 squared plus 4 squared, which take the square root of that, which gives us 5. So our unit vector u then is going to be the vector 3/5, 4/5. All right. Next thing I need is the partial derivatives. So I need to find the partial of f with respect to x and the partial of f with respect to y. So the partial of f with respect to x is fairly straightforward to find, right? If we go back to our function, we see that that's going to give me 2xy plus y squared, and the partial of f with respect to y is simply going to be x squared plus 2xy. So the directional derivative of u in the direction of u of f of xy is going to be the dot product of these two vectors. So I'm going to get 3/5 times 2xy plus y squared plus 4/5 times x squared plus 2xy. And doing the algebra, unless I made a mistake, I get 4x squared plus 14xy plus 3y squared, everybody over 5. And so we can evaluate that at any point in our domain. So next time, or next video, I should say, we're going to talk about the gradient. So as a promo, right, we've actually kind of already defined the gradient. We just didn't call it the gradient, right? So we wrote the directional derivative as the dot product of the vector formed from the partials of f with respect to x and y, and the unit vector u. And so that is the gradient. And we will do this next time I record. Have a great day.